Okay, folks, so here's a little answer key for this. Now, one thing that's not on here that you have to know is volume of figures rotated around the y-axis. So I just wanted to make sure that was clear. Over here, you can check that out on these days here. So rotating about the y-axis, make sure you know that because it's not on the review, but it is going to be on your quiz. So everything else is on here that we need to know. Okay, so first thing here, these first two are just old questions. So I'm going to pause, do those problems, let you look at the answers, but otherwise we'll get to the newer stuff. All right, so the first one, you got the integral from 1 to 3 area under this curve to the x-axis. That's what y equals 0 is. So you just set up your integral. 1 to 3, there's my equation. Raise the power up 1, divide by the new exponent. Raise the power up 1, divide by the new exponent. Raise the power up 1, divide by the new exponent. Plug in a 3, plug in a 1, subtract your answers, 101.3 repeating. Similarly, I have my lower limit and my upper limit. It's the equation area under this curve, so I just go through my rule. Raise the power up 1, divide by the new exponent. Raise the power up 1, divide by the new exponent. Sometimes it simplifies like that one. Raise the power up 1, divide by a 1, no big deal. And then you just plug it in, right? You'll plug the 3 in here, the negative 2 in here. Be careful with that negative that you're using parentheses all over the place. And then I'll pause this and do the answer. Alright, so our other problem worked pretty much the same. You just plug in the 3, then you plug in the negative 2, being careful to do minus a negative, which results in 33.3. So no big deal. That's good review. And it's good we did that because now we're going to start doing area between curves. Oh shoot, is that not on here? Oh, it's not. Gosh darn it. Alright, well, not the best one, but it's a good review of some old stuff. I do need to make sure you know the area between curves, so maybe I'll change one of these problems. Alright, so on this one, you have the integral of, I'm going to change problem 4 to be an area between curves kind of problem. So let me try that in a second. Let's do this one though. You got to set it up 1 to 2. See, there's your lower and upper limit of 1 over x squared dx. And the first thing you should do is rewrite that as x to the negative 2 dx. That'd be more beneficial because then you can do your trick. And notice I lose my integral symbol as soon as I do this trick. Raise the power up 1, divide by the new exponent. Okay, and then you plug in a 2 to the negative 1 over negative 1, and then you'll subtract off a 1 to the negative 1 over negative 1. Okay, and then once you get that, you'll get your answer. I'm going to change number 4 so it's better review for your quiz. Okay, so this one came out to be 0.5. Alright, so I'm changing number 4. I'm going to change number 4 to something that'll prepare you for your quiz. Because 6.1 actually had area trapped between curves. So I'm going to say find the area trapped between, let's get two curves. Let's say f of x is, let's go with radical, oh not radical, yeah, radical x plus 3, and g of x is going to be, let's see, hold on, let me come up with a good equation. Okay, I changed it a little bit. I'm going to change that to a 2 in front of here. 2 radical x and plus 3. And then I'm going to make this 1/2 x plus 4. I want the area trapped between those curves. Now you can't really do this problem without a picture. Kind of like here, I need a picture. So I graph them in my calculator. There's my two equations. I look at the graph and you can see there's an area trapped between them, right? So if I drew a quick sketch of that, I got this graph going like this. Okay, there's my radical x plus 3. Then I got the other guy slicing through here. Okay, so I'm looking for this area. Here's the problem. When you go to do your integral, the main part's pretty easy. Hopefully it makes sense that to find this area here, you want the integral of the top curve minus the bottom curve. Because if you just took the area of the top curve, it would be from that square root all the way down to the x-axis, and you're removing the part you don't want. So just to show you, if I took the area of the whole thing, it would be all this. And then if I take the area underneath my straight line, it would be this red part. Well, if I take the whole blue part minus the red part, I'm left with their overlap, or the area trapped between them. So right away, I already know my equation's going to be the thing on top, I'm going to write as negative 1/2. Or not negative 1/2, to the 1/2. So 2x to the 1/2 plus 3 is my top curve, minus, and make sure you use parentheses, 1/2 x plus 4. The problem is, and I can add those, I can combine like terms, like the 3 and the 4 are going to come together. Be careful that this minus sign goes to both those. But what's not here that you have to do a little extra work for is you have to find what number goes here and what number goes here. And that needs your graphing calculator. Okay? Because you have to find where they start and where they end. So I'm going to go second calc intersect. It's like this extra step. First curve enter, second curve enter. Your guess has to be pretty close. And it tells you 0.34 is your lower limit. 0.34. And then my upper limit, I do the same thing, intersect, and then first curve enter, second curve enter, but my guess has to be close. So I'm going to move my guess to be really close to this point. They meet somewhere up there. Boom. And it says, daw. Alright. I got to make my window bigger. Hold on. Zoom. I'll zoom out. Okay, geez, that's far out. Gosh. Okay, I can tell where they cross, so it's like right there. So I'm going to go second calc intersect, first curve enter, second curve enter, guess enter. There it is, 11.65. So 11.65. So you had extra work of how to find those numbers, where normally it's pretty much given to you. So this is the only thing that's different about these ones where I say find the area trapped between curves. You have to graph it. You have to do top curve minus bottom curve so you get their trapped area. And you have to do intersect to find the top and bottom. After that, it's just like every other problem. I should probably say 6, 6 if I round correctly. And then I'm going to do my exponents. So this is 2x to the 1/2. And I have minus 1/2 x, and then when I have a positive 3 and a negative 4, I get minus 1. So I'm just doing my rule on it, right? I do my trick, and I say, okay, raise the exponent up 1. So what's 1 bigger than 1/2? Well, you're adding 2/2 to it. So it's x to the 2/2, or sorry, x to the 3/2. And instead of dividing by 3/2, you multiply by its reciprocal, 2/3. Now, if there already was a 2 there, which there was, you just multiply it by the thing on top. Similarly, I'm going to have a 1/2 already going, okay, right? And then x to the second. Now, divide by the new power. If there already is a fraction, you're just multiplying it on bottom. And last but not least, minus 1x. 0.34, 11.66, and now I'm going to type in this whole thing with an 11.66 plugged in, and then a 0.34 plugged in. I'm going to subtract them. So let me pause it, do that. So that one came out to be 113.19. Once I plugged in the 11.66 and the 0.34, yada yada. All right, so we go to the back. These are just more practice problems, but then we get down here. So I'll pause, take a picture of the answers here. Okay, so here's the breakdown. Just take a pause, screenshot. This is more review of finding definite integrals. Now we get to the cool stuff from 6.2, which is spinning something around the x-axis. So in this, you just got to remember, instead of a normal integral, it's going to be pi times the integral of your radius squared. Okay, pi r squared because you're adding up a bunch of disks. So the first thing I like to do is draw what this would look like. So it always makes a mirror image if I'm spinning around the x-axis, and you give it a little, circularness. That's a word. Curvature. Anyway, this is half a sphere. Or if you cut an orange in half, that's basically what we're looking at. Alright, and we're finding the volume of this from 0 to 3. So don't forget the pi. So it's pi from 0 to 3. And originally this would be a brutal problem, except you remember it's radius squared. So if this is my radius of every one of these disks, remember it's slicing out little disks, which look like this, right? So if I took one slice of it, the radius of that disk is the height of your function, right? Well, guess what you get when you square square root? You get the original problem. Don't forget the pi. So the squaring of a square root just leaves you with 9 minus x cubed. That's a super easy thing to take the integral of. Don't forget the pi again. But 9 raise the power up 1 divided by the new one. X to the third becomes x to the fourth over the new exponent. And we still have a pi out front. And we're going to do with a 3 plugged in. And then we're going to do it with a 0 plugged in, which hopefully you know at this point gives you 0. So we're going to go 9 times 3 minus 3 to the fourth over 4. And you get 6.75 pi. So, which when I multiply that by pi, comes out to be 21.21 units cubed. So the volume of that half an orange is 21.21 units cubed, which is kind of cool. Alright, similarly, in this problem, we're going to have one with a hole in it. So this is called the washer method. So the washer method, we're going to, I still draw it, right? So I draw the mirror image, right? So imagine this thing spinning around the x-axis. It comes out of the page at us, it goes back down. So it really looks like, sort of like this. It looks like one of those funnels that you would spin a coin down. You know, if you've ever been to COSI, if you turn this on its side, the coin goes down and down and down and down. So yeah, basically it's like a hockey puck that someone drilled a funnel into. So here's what's bad about this one. If I took a slice of this, every single slice, right, imagine a disc here, every single slice has a hole in it. Even that final one, you can imagine it doesn't have a hole, but it does. So whenever you have one with a hole in it, it's called a washer method. And it's still just like, it's just like this, pi r squared, but if you have a hole in it, you have to do pi times the integral of outer radius squared minus inner radius squared. So if I looked at this, for this equation, first of all, I'm going from, I have to remember my pi, I'm going from 0 to 3 because those are the x values this is between. Okay, now the outer one, if you look at your radius, the outer part is this function, which is just that equation, y equals 9. So 9 squared is my outer, minus my inner, which is this weird curve, which is x squared squared. Don't forget to square it. I know if there's a square there, sometimes it's tempting to forget that. But then this becomes a pretty easy problem. So really the hard part of these problems is just the setup. Let me pause it, do the work, show you the answer. Okay, so after I get it set up, I raise it up a power, divide by the new one, and plug in a 3, plug in a 0, multiply it out, don't forget the pi. And then you get it. Boom! That was awesome. Alright, talk to you later, people.